Hello students, I welcome you to this session of Python programming. In today's session, we are going to discuss about the dynamic typing model in Python. If you have a C, C++ or Java background, you might be a bit confused about how Python uses variables without declaring them. So, for example, when we say type in an interpreter session or a program file, we type say a is equal to 3. Then how does Python know that whether a is an integer or a float or a string? And for that matter, how does Python know what a is at all? Because we have not declared a for its type. So once you start thinking about these things, you are discussing or you are into the domain that is known as Python's dynamic typing model. Okay. And remember, in Python, types are determined automatically at runtime, not in response to your declarations in your code. That means you don't need to declare the types of variables. They are automatically detected at runtime. So that would mean that you never declare variables ahead of time. And remember one thing regarding this Python variables, it just comes down to three things: variables, objects, and the links between them. So variables, objects, and references. Now, first we have a variable creation. So a variable like a name like a is created when your code first assigns it a value. So your variable is created when some value is assigned to it. Okay. And future assignments may change the value of the already created name. Now, variable type. A variable has never got any type information or any constraint associated with it. The type is of the objects which are assigned to variables. So remember the key: variables, they refer to a particular object at a particular point in time. Okay, and the variable use. So when a variable appears in an expression, it is immediately replaced with the object that it currently refers to, whatever that value may be. Further, all the variables must be explicitly assigned before they can be used. Okay, referencing unassigned variables results in errors. Now, let's understand when we say a is equal to 3. So we are saying assign a name to an object. Okay, so in the background, basically or conceptually, Python is performing three distinct steps to carry out your request. The first one is to create an object to represent the value 3. So first an object is created which represents the value 3. Then a variable a is created if it does not yet exist, because a might already be existing. If not, then it is created, and then a link is established between these two. So name a refers the object value 3. This is how the value is assigned in Python. Now, variables you can consider as entries in a system table with spaces for links to objects. So there is a table. On one side is a variable, and on the other side is the link to an object that it maps onto. And objects are pieces of allocated memory with enough space to represent the values for which they stand. And references are automatically followed pointers from variables to objects. So references are like pointers which join together the variables to objects. Now consider this example. Say a is equal to 3. So it's an integer. A is equal to spam, now it's a string. A is equal to 1.3, now it's a floating point. So we can say a starts out as an integer, then becomes a string, and finally becomes a floating point number. And it might appear to the user that the type of a changes from integer to string when we say a is equal to spam. However, this is not the thing that is happening. In Python, your variables, they have no types. Remember, types always live with objects, not with your variable names. So what we have done is we have simply changed a to refer to different objects. Here a is referring to an integer object 3. Here a is pointing to a string object. Here a is pointing to a floating point object. So remember this bottom line, that a variable in Python is that it references a particular object at a particular point in time. Remember this is very important. Now there's something known as a shared references concept. So for example, if you have a is equal to 3 and a is equal to spam, okay, right? So the answer is that Python, whenever a name is assigned to a new object, the space held by the prior object is reclaimed if it is not referenced by any other name or object. Okay, so when A is 3 and then you assign this object spam to A, then this 3 is now not needed by A. So if it is not, this object is not associated with any other variable, it can be reclaimed by the Python's memory system. And this concept is known as garbage collection. This concept is there in all programming languages, that is freeing up of unused memory space, and it makes life much simpler for programmers. Okay. Now let's take another example of shared references. Okay, so let's say A is equal to 3 and B is equal to A. So we start with this assignment. So first this object 3 is assigned to A and this A is assigned to B. Okay, so that means that A or B are now referring to the same object, that is 3. Okay, now let's explore this further. Suppose A is 3, B is A, and now A is spam. That means A is no longer pointing to this object 3. So what will happen to B? Well, B will still point to this object, only that the A's reference has now moved to spam. It is dissociated from this object 3. And the value of B still references the original object, the integer 3. The resulting reference structure is there in front of you. Very important for you to understand, because it would be there for all your future assignment operations with the various types in Python. Now let's take another example. I'll be taking a list which is a mutable object. Okay, mutable is something which can be changed, and immutable is something which is unchangeable. So I've taken a list or an array that you understand in C, C++ or Java. Here is the same thing. L1 is a list. A list is something which can be changed, is mutable, and L2 is now referring to L1. Okay. So let's suppose I change something in L1. I'm changing the first element of L1. So L1 0 is equal to 24. So L1 0 is 2 right now. I convert it to 24. So if I print L1 now, it is 24, 3 and 4. And if I print L2, obviously it is also the same, because it is referring to the same thing. So when you change a part of the object with which a variable is referring, it is known as an in-place change. Okay, so let's revisit this example in another way. Let's say the list L1 is 2, 3, 4, and I make a copy of the list. Now I'm not making the reference same, I'm making a copy of the list. So a copy of the list can be made by using this syntax. With this syntax we'll learn in future, don't worry about it. Or we can also make a list like this with these syntaxes also. Okay. Then I change the value of the first element of L1, that is 2, now make it 24. So if I print L1, it is this. If I print L2, then L2 remains unchanged, because L2 is not a reference, this thing, it's simply a copy of L1. And when L1 changes, then L2, which is simply a copy, which is not a reference, it stays the same. Okay. And now let's see this one very important example, and then I'll work out all these things on the Python interpreter for you. For example, the variable x is having a value 42, and if I assign a value shrubbery to it now, then is 42 reclaimed by the Python's garbage collector? Okay. Now what Python does integer is an immutable object in Python. So Python caches and reuses small integers. It does not reclaim it. Garbage collection process does not reclaim integers. Okay, so the object 42 that was here is not probably not literally reclaimed. Instead, it is likely to remain in the system table to be reused the next time you generate a 42 in your code. Okay, so we'll explore this concept soon in the Python interpreter. Now let's take two lists, L as 1, 2, 3 and M as 1, 2, 3. So obviously L and M are two different objects. Okay, L and M are two different objects. Although their values are same, the list values are same, but they are two different objects. So if I try here L equal to M, it will return true. But if I try something like L is M, then it will return false, because L and M are different objects. Okay, that's the same thing I carry out with integers. Say x is equal to 42 and y is equal to 42. And if I check the values, then the values, it returns true. And if I check their types, okay, even then it returns true. That means x and y, they refer to the same object. Okay. When you are putting say x is equal to 42 and y is equal to 42, that means you are creating two different objects, and two different objects should be there in the memory. But what Python does, it retains this integers in its cache, and it does not reclaim it, and uh, the x and y here are referring to the same object in the memory. Okay, we can understand this with the help of the get reference count in sys module, whether this thing is true or not. Okay, I'll make it I'll show it to you. But let's now first try this example, the last one that we have understood here, LNM, this one. So let me begin a Python session for you and say L is equal to 1, 2, 3, M is equal to 1, 2, 3. So I'm taking two distinct objects. So if I say check the values, it will return true. But if I say check L is M, it will return false. Why false? Because they are different objects. They have got different identities. So you can check their IDs by this ID function. So this is the memory ID for L, and this is the memory ID for M. So you can see that the IDs are different. Okay, but like I said, if I use say x is equal to 42, y is equal to 42, if I check their IDs, okay, then you can see that their IDs are same. Okay, for small integers, Python is reclaiming its variables. It's not reclaiming its variables, it is putting them in a cache for further use. Okay, is that fine? So if I check something like x is equal to y, it's true. But if I check x is y, even that is true, because they are the same objects. Okay, so how does this happen? So let's go to this part of our presentation now, the last one. Now this there is a get reference count in sys module, which tells you that how many times an object has been referenced by the variables. Say for example, let me run this code for you. Import sys, and let me just print this for you. Okay, so I'll import sys here. Okay, and I will run for you sys dot get reference count of what example? Okay, let's say 30. So it is showing 17. That means 17 variables have referred to 30. And this 30, this object is not reclaimed by the Python's garbage collection process. It stays there, and whenever it is required, it can be used. So let me use it now. Let me take another variable, say a equal to 30. So this is another reference to 30 now. So what should be the reference count? Obviously 18. The reference count has increased. One more variable has referred to this object which is there in the memory. Okay, fine. So this is the get ref count, and you can see how your objects are being referred to in the memory. Okay, and this concept is also very important, that small integers or immutable objects like integers, they are not reclaimed by Python literally, and they remain in the system table to be reused next time when you want that value or that object. Okay, so let's have a quick recap with a few references here. So when you say a is equal to 3, b is equal to a is equal to swam, first a is pointing to object 3, now b is pointing to where a is pointing. If a starts pointing somewhere else, b still points to that object. So b is still pointing to 3, whereas a has now started pointing to this object spam. Okay, so this is all regarding the dynamic typing model in Python. Very important concept for you to understand it, so that you can work around with certain types that we're going to learn in future, like lists, sets, tuples and all. So that is all for today's lecture, guys. Keep learning, keep watching the videos, and if you have any problems or any comments, you must put those comments in the comment section of a particular video. So goodbye, take care.